Okay, good. It's recording. All right, so from the beginning, there we go. Okay, so let's get started with some actual content. So again, we're really going to spend most of today just sort of introducing structural equation modeling. What is it? Why do we care? Maybe you already know that because you signed up for the class, but we'll do a brief review of what structural equation modeling is and what some of the advantages of SEM are, and then we'll start talking about some basics of path analysis. Okay, so what is this thing called structural equation modeling? So structural equation modeling really refers to a whole family of techniques where we actually analyze covariance matrices to explore relationships among a set of variables. And I should actually maybe just pause for a minute here and say that some of the structural equation models that we will talk about, especially in the first half of class, actually, the first half of class, the structural equation models that we talk about really only require the covariance matrix. So everything we do will be sort of thinking about variances and covariances and how to really, use that covariance matrix to model the relationships among different variables. Later in the semester, we're actually going to bring means into the equation, no pun intended, or pun intended. So we could also use the variance covariance matrix and a vector of means and to actually model data. So it's kind of interesting because the first, we spend a lot of time in other stats classes thinking about means, right? And actually for the first several weeks of this class, we're not going to think about means at all. We're only going to think about variances and covariances, but means will come back in the second half of the semester. So, here where I say analysis of covariances, it's totally true for the first half of the semester, and then actually in the second half of the semester, we're going to analyze covariances and means. So SEM is a really versatile method, though, that allows us to test we can test very specific hypotheses that involve systems of latent variables. And we can get much more sort of pointed and much more specific about our hypotheses than we are able to in a lot of other sort of traditional techniques. I mean, if you think about what we do with hypothesis testing in a lot of other classes, we just say things like, difference in the means is 0, right? Or whatever. We can actually, in this class, we're going to learn how to set up and test competing models, which I think is a much more interesting way of sort of thinking about how we sort of make an argument or make a case for our model, right? So rather than just sort of saying, well, the correlation isn't 0, or the difference isn't 0, we're actually going to, potentially put together two different models and say which of these two models, appears to fit, or does the data fit model A better or model B better, right? What's the model data fit? How does that look across these different models? Which is a much more sort of, I think, nuanced way of thinking about how we do these analysis, how we analyze data. So it's really versatile. We can use structural equation modeling to study very complex patterns of interrelationships among variables, to compare different groups to each other. We can model latent means. We can study change over time. We can do a whole variety of longitudinal analyses using SEM. We're just going to scratch the surface in this class in terms of the kinds of longitudinal analyses that we can do with SEM. So lots of fun. So what are, I've alluded to some of these advantages, but some of the advantages of SEM are that we can really specify our models a priori, and then we can assess the degree to which the data fit the specified model. And I see that as a huge advantage. And especially, if you sort of think about what's going on right now in terms of, thinking about, reproducibility and replicability, right? And, trying to be sort of better critics and stewards of our own work. I mean, when we think about this idea of setting up a model a priori and then assessing the degree to which the data fit the specified model, I mean, I think that's a good way of sort of setting up our analyses. You know, we can use SEM to test these existing hypotheses about relationships between not just observed variables, but this is a huge advantage, latent variables too. And we haven't even really talked about what latent variables are, but latent means unobserved, right? So a latent variable is a variable that you don't actually directly observe, but you but you believe it, to be true, right? It's the variable that you're interested in. And in the social sciences, we work with a lot of latent variables all the time. So for example, creativity is a perfect example of a latent variable, right? I mean, I heard somebody say they're interested in studying creativity, right? But you can't open somebody's mouth and pull out creativity, right? You can't directly assess creativity. What you can do are come up with a series of assessments that you think, okay, creative people would do better at this, right? This would be an indicator. This task is an indicator of somebody's creativity. So you build a whole set of tasks or tests or assessments that you think are actually indicators of somebody's creativity, and then you can use that information to fit a latent variable model where you say, okay, the latent variable is creativity, and it's creativity that's actually predicting people's responses to all of these different tasks or to all of these different items. There are some huge advantages to using latent variables instead of observed variables. One of the biggest is that we can directly sort of deal with measurement error, which is something that, again, in a lot of other classes sort of gets skirted under the rug a bit. I mean, it's one of the, if you think back to your multiple regression class, one of the assumptions of multiple regression is actually that the covariates are measured without error. But usually that isn't usually belabored in the regression class, because if you thought about it too long, you'd realize how absolutely unrealistic it is to assume that all of your independent variables are measured without error, right? But that is an issue. And in fact, if the measurement error, if you just have a simple regression, the measurement error in the independent variable is actually going to attenuate the relationship between the independent variable and the dependent variable. Once you have a larger system of equations, it gets a little bit trickier to predict, exactly what the direction of the bias is going to be. But certainly you don't get unbiased estimates of those regression coefficients if you have measurement error. So latent variable modeling actually gives us a way to directly deal with this issue of measurement error. And so instead of using the observed variable as a predictor, we use the latent variable as a predictor. And the latent variable is, again, it's latent, it's sort of error-free, right? It's net of measurement error. So that gives us a way to actually get a much sort of truer, better estimate of the relationship between that variable and some other variable. So using latent variables is a huge, huge advantage. I will talk about that throughout the semester. Again, SEM allows us to test competing theoretical models to determine which model actually best reproduces the observed variance covariance matrix. We can use SEM to model direct, indirect, and total effects in a system of variables. So we can use SEM models. I mean, SEM models are perfect for thinking about issues like mediation. If you have a mediational model, I mean, SEM is probably the easiest, best way to tackle simple and more complex mediational models. All right. So I already said this, actually got ahead of myself, right? But we can use latent variable models, which correct for the unreliability and provide more accurate estimates for the effects of the predictor on the outcome or the criterion variable. And this is an incredibly, incredibly flexible framework. So as I said, we're going to start a little more simply, but once we get all these tools under our belt, we'll be able to look across time. We'll be able to model. We'll be able to, model across groups. We'll be able to look at whether groups are similar and different in a lot of really interesting ways that aren't maybe, again, aren't even ways that you're probably used to thinking about between group differences. Okay, so how are we going to do all this? Well, Klein sort of talks about some basic, these are really basic steps in SEM. So just sort of overarching, what do we want to be thinking about as we sort of approach this modeling? And the first thing is, we're always going to have to start off with what's our model? So, and that's sort of the specification stage. So what is the model that we want to fit? Which again, I think is a really good to sort of stop and think about your data in that way, right? I have these data, I have this, what is the model? What is the model that I'm trying to fit, right? And what is my model, what does my model say? What does my model theorize? So this specification phase is more involved in SEM than it is probably in a lot of other sort of, maybe some of the other statistical techniques that you're familiar with. So, okay, so first we're going to figure out what's my model. Then the second step is, can that model be estimated? So again, once we sort of get started, and I'm going to show you sort of how you can draw, sort of draw path diagrams to draw pictures of models. It is possible you could draw a picture of a model that can't actually be estimated. So I'm going to teach you the rules of the road in terms of model identification, right? What kinds of models are uniquely identified so that we can actually, are identified so that we can get unique estimates for our parameters, and what models aren't identified. So again, and we'll talk more about identification this week and next, but that's sort of the next step. Okay, what's my model? Can it actually be estimated, right? Is it identified? And then the next step is estimation. What statistical technique am I going to use to estimate this model? We're not going to talk a ton about estimation. For this class, we're going to use maximum likelihood estimation as our sort of our default estimator for just about everything we do. I will talk a bit in the coming weeks about what maximum likelihood estimation is and sort of how it works. But there are other ways to estimate structural equation models besides maximum likelihood estimation. And from time to time, I'll make reference to those. But really predominantly, we're going to be using maximum likelihood estimation, which again stands in stark contrast to regression. In regression class, you used ordinary least squares as your estimation technique. And here we're not generally going to use OLS. We're going to use maximum likelihood. But okay, so that's your sort of next step, is to think about, okay, how I'm going to estimate this model. And then the next question is, okay, well, how did my model do? Is my model right in quotes? There's really no, I think the more you do modeling, the more you'll notice that, there probably is no such thing as a totally like the right model. Box famously said, all models are wrong, but some are useful. And I think that's a really good adage to live by. I mean, having said that, some models are more wrong than others, right? So maybe we want to think about getting the right test model, like the best model we can. Every model is a simplification of reality. Reality, I mean, this is like, we could sort of get into like thinking about, qualitative research versus quantitative research, right? In quantitative research, we tend to be pretty parsimonious. We want to find some big ticket item things that, explain the world that we're seeing, right? In qualitative research, often people are really sort of diving in and going into a lot of depth to sort of really explore the nuances and the complexities that exist, right? again, you can't build a statistical model that will be a perfect fit for every unique person and all of their, for every person in every scenario. If you try to if you try to build a model that takes into account every possible variable and every possible thing, then, you get a model that's so complicated that it's not, it's not usable, right? It's not even useful. So every model that we fit is going to be a simplification of reality, right? But is it useful? Is my model useful? So is my model, again, how's my model performing? In structural equation modeling, when people talk about model fit, they're really talking about the ability of the model, and again, we'll talk about this in way more, like lots of depth over the next few weeks, but they're really talking about the ability of the model to reproduce the variance covariance matrix, right? So, again, everything we do is going to be about variances and covariances, and how well can my model actually reproduce the variance covariance matrix. Now, I just want to throw out a caveat, which again, I will mention as we go through the semester, which is that just because I can reproduce the variance covariance matrix doesn't actually mean that I'm doing a good job explaining anything. So you might have a model that fits really well, but has very little predictive power. And when I talk about prediction, I'm thinking about prediction in the traditional R-squared kind of framework, right? In a multiple regression, you have a model, you've got some predictors, and you look at like how well do these predictors actually predict the outcome variable of interest. The R-squared is the proportion of variance in the criterion variable that's explained by your set of predictors. We get R-squared in SEM as well. Now, we might not have just one dependent variable anymore. We'll often have lots of variables that are dependent variables, but we do get R-squared measures. But I just want to, sort of caution you that when people think about model fit is really about the fit of the model to the data. So can I reproduce that variance covariance matrix? It's not about, do the independent variables actually predict the dependent variables, which is also really, really important. So again, I will keep bringing that back to the forefront. Don't just think about model fit, but also think about the utility of the model as well. And then, to sort of Klein's 4 steps, I'm going to add interpretation. And we'll spend a lot of time talking about interpretation, and a lot of your homework will be about making sure that you can actually do some basic interpretations of models. So what does this model mean? What are the parameters that come out of this model mean? How do I interpret them? All right, so let me pause there for a second. Are there any questions about anything that I just said? So I want to sort of get us on the board with some basic vocabulary that's going to be really important as we move through the semester. So in multiple regression, we're really used to thinking about independent variables and dependent variables. And I've even been using those terms here today because we hadn't done this vocabulary yet. But I'm going to reframe sort of the way that we think about variables, and instead of talking about predictors or independent variables and criterion variables or dependent variables, we're going to talk about exogenous variables and endogenous variables. So an exogenous variable is your traditional predictor for multiple regression. But what's important here is an exogenous variable is not caused by any other variables in the model. So it predicts other stuff, but it's never predicted, okay? And so I say here paths lead away from those variables, but never toward them. We haven't seen a path diagram yet, so maybe that doesn't make a lot of sense to you, but just think of this as any independent variable you had in a multiple regression, framework, those would all be exogenous. They're only predictors, they're not predicted. Okay, so where things get a little bit more interesting here in SEM is that I can have a variable, again, in multiple regression, everything was either a predictor or it was a criterion, right? But here I can actually have a system of equations. I can have a system of, different variables. Just think about a really basic mediational model where you have like an X variable predicts, a mediator, right? The mediator predicts the Y variable. Just even in a simple mediational model, you have this sort of intermediate variable. A mediator is both predicted by the independent variable, but it also predicts the outcome variable. So is it a predictor or is it a criterion variable? Like from the standard multiple regression framework, it's both. It's a predictor of the outcome variable, but it's predicted by the independent variable. And so that's why we don't use the terms independent and dependent variable so much anymore, because what we really have are variables that are not predicted by any other variables. Those are our exogenous variables. And then we have endogenous variables, which are predicted by at least one other variable. And an endogenous variable could be something like a traditional criterion variable in multiple regression, where it's predicted by other variables, but it doesn't predict anything else. Or an endogenous variable could be a variable that's predicted by other variables that is itself a predictor of some other variables. But that's the key distinction when we're thinking about variables. It's like, well, is it exogenous? Is it sort of outside the system, just predicting in? Or is it endogenous, which means it's really sort of in our system of equations as a criterion variable for at least one other variable? Does that make sense? Okay. All right, so our next term that we're going to talk about here is disturbance. So a disturbance is really a residual, and the disturbance or the residual is basically the sum of all of the unexplained effects. So again, in a regression, if you think about, I'm going to have to, hold on, let me see if I can do this. Yeah, that's fine. Aha, hey, I made the transition. Okay, so we were talking about disturbances, right? Let's see if this works. Can you see me drawing? All right.
Yep, we can see the drawing.
What?
We can see it.
Oh, okay, good. So let's say this is my X variable. This is my oh, I didn't mean to, hold on, now I need, where'd my eraser go? There it is. I'm making stray. It's a lot harder to draw on this than it is on the blackboard, but I'll get better at it. Okay, so here's my X variable. I'm just going to draw what is actually a simple linear regression here. Okay, so this is my X variable, my predictor, and here's my Y variable, my criterion variable. And we would normally, oops, here we go. And this is my disturbance. That D is my disturbance. So if you think about in a regression model, right, you have, this is my regression coefficient here. It's my B or my beta if it's standardized. I keep putting my finger down there. Okay, there we go. So there's some, think about the variance, the variance in Y. Some of the variance in Y is predicted by X, right? And this regression coefficient is actually telling me about the strength of the prediction there from X to Y. But some of the variance in Y is not predicted by X, right? And that's really what this disturbance term, this residual, is capturing, the fact that not all of the variance in Y is predicted by X. There's some unexplained variance in Y. And that's really what the disturbance variance is. The disturbance variance is the variance in Y that isn't predicted by X. Now I could have, and again, now I'm making this a multiple regression. So if this is a multiple regression, looks something like that. So now I have X1 and X2 are predicting Y, but again, still the disturbance, this D1, this disturbance term is still the piece of y that isn't predicted by x. By the way, I should, as long as I'm drawing this, if I want to be really complete, I can draw this little two-headed arrow there to indicate that this x variable has a variance. Okay, so this double-headed arrow is saying, okay, this is the covariance of x with itself in some sense, so that's the variance of x. And there's also a variance, there's a variance of x1 and there's also a variance of x2. And these variances, these are just like, you could just compute the variance of x1 and the variance of x2 in your favorite software package really easily, right? These are, because again, these are exogenous variables. So, there's some variance there that we can estimate. It can be a parameter in our model, but there's nothing very complicated about this, right? And here I'm just saying x1 and x2, this curved arrow is just saying x1 and x2 are correlated with each other, or they covary with each other, right? So this curved arrow, and we're going to do a lot of drawing in this class. So in this path diagram, this curved arrow is a covariance when it's unstandardized, and it's a correlation when it's standardized. Because remember that a correlation is just a standardized covariance, right? So in a normal regression model, we always allow all of the independent, we don't think about this, okay? But all of the independent variables are allowed to correlate with each other. And we do think about it in the sense that we talk about multicollinearity, how correlated are the independent variables with each other, right? But, when you're fitting a regression model, you don't usually literally say when you're writing the code for the regression model, hey, make sure all my independent variables are correlated with each other. That's just something that happens by default in any package that's fitting a regression model. Whatever independent variables you put in the regression model are assumed to or allowed to be correlated with each other. So that's really, when you see a curved arrow, too dark, let's start my curved arrow over again. When you see a curved arrow in SEM, curved two-headed arrow, that just means these two variables correlate with or covary with each other. But there's no direction, sort of no directionality to that. When we see an arrow like this, that is sort of a straight one-headed arrow, that indicates something like a traditional regression path. And there is, again, when I say directionality, I don't necessarily mean that it's a causal path. Causality, to infer causality is a more complicated issue, more complicated game that we'll talk a little bit about in this class, but not too much. Well, somewhat. But what I mean is this path is now a regression path, not just a simple, bivariate correlation. So how is that regression path, that B1 path, how is it different here than if I just allowed X1 and Y to be correlated with each other? What's different about this B path? It's the effect of X1, the effect of X1 on Y after controlling for X2, right? And that's really, really, really important. So this B1 path, again, right now this is just a multiple regression model. These models. I'm just drawing it in a sort of a picture for you. So right now, this B1 is the effect of X1 on Y after controlling for X2, right? And B2 is the effect of X2 on Y after controlling for B1. So these are, again, these are sometimes called, you'll even see this written sometimes, they're sometimes called causal paths in SEM in the sense that they are directional paths. But again, that doesn't necessarily mean that you can infer causality there. Okay, back to our residual. Oh, no, I didn't mean to do that. There we go. Back to our residual. So the disturbance is just the variance in Y that isn't explained by X1 and X2, right? So I have this B1 path that you know, helps. I understand how X1 predicts Y after controlling for X2. I have this B2 path that tells me about how X2 predicts Y after controlling for X1, right? And I have this disturbance. I have this disturbance variance, which is just the variance in Y that isn't explained by X1 or X2. And notice that I don't have a little double-headed arrow for Y in my path diagram. That's because that's not actually a parameter in the model. I'm not actually, what I'm doing is I can recreate what the total variance in Y is by looking at how much of the variance in Y is explained by X1, how much of the variance in Y is explained by X2, you know, how much do X1 and X2, how much do they relate to each other? And then also, you know, how much of the variance in Y isn't explained by either of those variables. And once I know all of that, I can use all that information to actually basically recreate what the total variance in Y is. But the total variance in Y is not a parameter in this model. It's the unexplained variance in Y. Does that make sense? But again, this is just a regular multiple regression model right now. Okay. Let's see here. Do I want to save that document? No, I don't think I want to save that document. Now I have to go back to my PowerPoint. This is where it's a little bit more cumbersome. Hold on a sec. Oops. Share content. There we go. All right. You can see that, right? Yep. Okay, so the disturbance is really just, you know, it's the piece of Y that isn't explained by any of the variables in our model. Now, might be explained by other variables. They're just not in our model, right? So there could be other variables that aren't in our model that explain this variable. Or it could just be total error. And in fact, it probably is both, right? This disturbance is probably a combination of, there is probably some error in that variable. And then there probably are other variables out there in the world that could explain some more of this variance, but they just don't happen to be in my model. So every endogenous variable in a path diagram or structural model is going to have a disturbance term. It's going to have one of those D's, and we can estimate the disturbance variance. So it's like an error term, but again, it represents all the unspecified causes and all the error in the structural equation. And it could end up being correlated with one or more causes or with other disturbances. More about that later in the semester. We're not going to talk about more about that right now. And you know, in that diagram that I drew, it has an implicit coefficient of 1. So the path from that disturbance, remember I drew a little path from there was like a circle with a D and then there was a path. I didn't actually put anything in that path, but we're always going to constrain that path to be 1. So we're going to constrain the path from the disturbance to the outcome variable to be 1, and we're going to estimate the variance, the disturbance variance, which again, I think this will make more sense when we kind of get into this. Okay, so what are our standard symbols for path analysis? An oval or a circle represents a latent variable. So anytime you see a nice round circle or an oval, that's a latent variable. And if you see a square or a rectangle, that's an observed variable. So we're going to use, when we draw these path diagrams, we're going to use this kind of setup. So we know that anything that's like a square or rectangle is observed, and anything that's a circle or an oval is latent. And the easiest way to think about latent variables sort of most generally is, this is a variable that you wouldn't find in your data set, right? If you look in your data set and you've got, you know, scores on, I don't know, scores on the Torrance test of creativity, and you've got scores on, I don't know, whatever, this math assessment and this reading assessment, any of those scores that are in your data set, those are observed variables, right? But a latent variable is not going to be sitting in your data file. If it's sitting in your data file, it's observed. It's not latent. So I think that's kind of an easy way to start thinking about, is something a latent or not a latent variable. Now, usually for residual or error terms, we also use circles because they are actually latent variables. Residuals or error terms are latent variables. They're not in your data file, right? So they are latent. But often you'll see that the residual or the errors, they often have smaller circles, sort of indicating they're not necessarily your like conceptual latent variables of interest. They are still latent, but they're sort of these latent errors. As I said, a single-headed arrow is a path, which is like a regression coefficient. So think of a path as being basically, it is the same. At this point, it's totally the same, but it's basically the same thing as a regression coefficient. And think of a double-headed arrow as being indicative of a covariance. And if we standardize a covariance, we get a correlation, right? So it indicates a covariance, but it also can very easily then give us the information about the correlation between two variables. So these are the standard symbols that we're going to use for path analysis. Does that make sense? All right. So here we go. Here's just another example. So here we've got a multiple regression model with 3 predictor variables as a path model. So here the disturbance I've just called E, because often in a regression we call it E, right? So I've just kind of called it E instead of D here. But we've got a multiple regression where we've got 3 predictor variables, and you can see that all 3 predictor variables are correlated with each other. In this drawing, I have not done the little double-headed arrow to indicate that we have that we're actually estimating a variance for each of these variables, but we are estimating a variance for each of these variables. We have 3 paths, which are like, these are going to, we'd have 3 regression coefficients for the effect of motivation on GPA after controlling for academic self-perceptions and self-regulation, right? Same with academic self-perceptions, predicting GPA after controlling for motivation and self-regulation. And the same, we'd have self-regulation predicting GPA after controlling for motivation and academic self-perceptions. So we have these 3 paths that are telling us about sort of the independent contribution of each of these variables after controlling for the other variables in the model. And then you can see that I've written this out as just a regular multiple regression equation where we have, y sub I, which would here would be GPA, right, is predicted by, we've got an intercept plus, the effect of motivation on GPA after controlling for everything else, that, right, so that's the beta 1, x1 sub I, and so on and so forth. And then the E sub I is really our error term, right? And we can actually then estimate the disturbance. Let me say the disturbance term. I want to say disturbance here, even though it's an E. So that's really our residual or our disturbance term. And again, we can compute what the variance of that disturbance is. So there is a residual for every person, right? Just like we have in multiple regression. A person's y-score is a function of this whole equation, and then there's some residual, which is the difference between the person's actual score and their predicted score, right? And we get that deviation for every person, so we get a residual for every person, and if we take the variance of those residuals, that is the disturbance variance. And again, our normal assumptions in multiple regression are that all of our independent variables are measured without error, which I said is not a very reasonable assumption, but it's an assumption that we make. We also make an assumption of linearity, which means there's a linear relationship between these independent variables and this dependent variable. So, as for it to be linear, that means as motivation increases, right, GPA increases, or as motivation increases, GPA decreases, but we don't have some sort of a curvilinear relationship where, like, at either high or low levels of motivation, you find lower GPA than you do when you have sort of mid-range motivation, something like that, right? We make, now again, there are ways to model nonlinearity. So, and we will talk about some ways to model nonlinearity, but we're making the assumption that we have a linear relationship in this model. And we're also making the assumption of independence of observations, right? So for those of you who've taken multi-level modeling, we're not dealing with clustered samples here. We're assuming that all of our observations are independent of each other. There are ways to combine structural equation modeling and multi-level modeling, or to do structural equation modeling with clustered samples. But right now, for simplicity, we're just going to assume independence of observations because we have to run before, or we have to walk before we run. We want to run before we walk, right? Okay, so a little more vocabulary. There are a couple different types of SEM models. And this is important. People refer to recursive and non-recursive models. In fact, I even said non-recursive models when I was talking about the models that we'll cover. So everything that we do right now for the next couple of weeks, we're really only going to be talking about recursive models. In recursive, and these are the most common models, and they're the sort of the easiest to fit. There's some nice simplicity that comes from recursive models. So in recursive models, the disturbances are uncorrelated with each other, and all of the causal effects are unidimensional. So there are no feedback loops. And what that means is that when we put together all of everything we're doing, when we put together a model as a set of equations, you can list that set of equations so that no cause is actually going to be an effect in a later equation. So going back to, let me go back here for a second. So this is a perfect example of a recursive model, right? There's, these three things are sort of, again, I'm using cause very loosely here, but right, these are predicting GPA, but there's no sort of way in which GPA is then sort of cycling back and predicting one of these variables, right? But imagine if I drew a path, I can't draw a path right now on my PowerPoint, but imagine I drew a path from GPA sort of coming back and predicting motivation. Well, that would be weird, right? But that's what I'm talking about in terms of like a feedback loop. So let's go to this picture in this next picture. This is a picture of a non-recursive model. So if you look here, this is job satisfaction and family satisfaction. And you can see job satisfaction is predicting family satisfaction, and family satisfaction is predicting job satisfaction. And then actually the disturbances U and V are also correlated with each other. So we're saying, and these are cool models. This is a non-recursive model that has a feedback loop. So it's basically saying like, hey, the happier you are at your job, the more satisfied you're going to be at home. The more satisfied, it also says though, hey, the more satisfied you are at home, the happier you're going to be at your job. But if you think about then that, what does that mean then? Like the more satisfied you are at your job, the happier you are in your home, the happier you are in your home, the more satisfied you are in your job. You can see that there's kind of a feedback loop there, right? These things, there's kind of like there's this sort of looping that's going to happen. Boop, 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 boop. So this is one example of a non-recursive model that actually has a feedback loop. It also has correlated disturbances here. So in this case,
Amanda popped into the chat and said, I would think that GPA would loop back to influence academic self-perception.
Yeah, it's a really good point, actually. And there's a lot of research actually about which comes first, academic self-perception or academic achievement. And a lot of those models actually are over time. I mean, the best way to study something like that is to get multiple time points. So you collect academic self-perceptions at multiple time points, and you collect achievement at multiple time points. And then you can actually you can fit sort of like cross-lag models where you sort of look at, after controlling for prior achievement, does prior self-concept help predict subsequent achievement? So anyway, we will talk about models like that later in the semester. I think that's a really, really good observation. But for right now, that picture is just an example of a simple, you can't really do that if you only have, you can't get very far if you only have everything at one time point, right? Which is sort of that example. So that was an example of a recursive model, but you're absolutely right that that's not the best way to tackle that kind of problem. And this is our example of a non-recursive model. So anyway, So non-recursive models have feedback loops or correlated disturbances. When you have non-recursive models, things get a little bit more complicated. So we're going to wait, we're going to wait till later in the semester to really dig into non-recursive models and how those things get a little more complicated. But I think it's important for you to be able, at this point, to be able to recognize whether a model is recursive or non-recursive. And again, know that we're really only going to tackle recursive models right now in terms of thinking through identification and specification. And we'll come back to non-recursive models later. But a recursive model, everything's kind of going in, everything's unidirectional, everything's going in one direction. And in a non-recursive model, we either have feedback loops or correlated disturbances or both. So you've got sort of this doubling back. All right. We're doing on time, by the way. We're doing okay. So let's take a look at this picture. So which variables are exogenous and which variables are endogenous? And then can we actually write a set of equations to sort of express y and z? So could you write an equation to express what's going on with y, and could you write an equation to express what's going on with z? Which kind of gives away the first part of the answer. So which variables are exogenous here? Anybody?
X1 and X2.
Yeah, X1 and X2 are exogenous, right? And Y and Z are endogenous, right? So can we write an equation to sort of say, how is Y predicted? And can we write an equation to say, how is Z predicted? And then actually, we could theoretically combine those equations. So take a second and see if you can, I'll give you a second to see if you can write those equations on your own, and then we'll do it, then we'll look at them together. I should get myself a piece of paper, by the way, just so I have one. I'll be right back. Okay, I'm done. So I'm sure you're all done too. Okay, so let's take a look at this. So the first thing we do is we say, okay, well, y is equal to a, right? This is just and this is the parameter we're going to estimate here. A, x1 plus b, x2 plus u. Does everybody see why that's the case? That y is just equal. Again, think of these are just like these would be like regression coefficients. I'm just using, a and b, or it could be b1 and b2. It doesn't really matter, but these are regression coefficients. So y is equal to a times x1 plus b times x2, right? Plus u. And these are like the three sources of variance in y. So there's going to be a piece of y that's explained by x1, a piece of y that's explained by x2, and a piece of y that is left unexplained. Okay, and then when we think about, oh, I didn't mean to go, hold on, let me go back. Then when we go to z, this is pretty easy. Z is equal to cy, right? It's regression coefficient cy plus v. So z is just predicted by y. But we can actually substitute this whole term, ax1 plus bx2 plus u, we can substitute that in for y, right? Because we just said we've broken up y into three sources of variance, this, and this. So if I substitute this whole thing for y, then I'm saying z is equal to c times, take this and substitute it for y, right? So I plug in c times ax1 plus bx2 plus u plus v. And now I need to actually just do a little, right, the distributive property. So I get z equals cax1 plus cbx2 plus cu plus v. And so now what I've done actually is I've expressed z as a function of just the exogenous variables. Notice that when I substituted that term in for y is no longer in the equation at all, right? So this now I've got z expressed as just a function of x1 and x2. And this is actually really, an important idea that's going to underlie all the mediational models that we end up doing. So right now we're just understanding how to sort of draw path diagrams and write them as equations. And I want you to be able to see equations and take those and turn them into path diagrams. And I want you to be able to take the path diagrams and turn them into equations. But, we'll come back and get into the meat of mediation later. I saw that Fayez asked, what are those ones above the y and the z? Yeah, those ones are a little bit misplaced. I sometimes have trouble drawing. They should really be on the arrows there. Because remember, I said that the path from u to y is actually constrained to be 1. We constrain the path from u to y to be 1, and then we estimate the variance of u. But depending on which program I use to draw things, sometimes they get a little bit a little bit put to the side. So we're not actually estimating paths from u and v to y. We're just estimating those disturbance variances. But that was a good question, Fayez. Any other questions? Well, let me see what our next thing is. I'm conscious that we should take a break. I'm just trying to think about, let's do like another slide or two, and then we'll take a break when there's like a good natural breaking point. Let's see something here. Okay. So the standard specification, there are actually a couple different specifications for path models. We're going to talk about the standard specification. I don't even know if we talk about the other specification. We don't really need to right now. So in the standard specification, measures are in their original metric. The disturbance paths are fixed to 1, which is what I was just talking about. And the disturbance variances are freely estimated. So in the standard specification, we fix the paths of the disturbances to 1. We estimate the variances. The other specification that's sometimes called like the path analytic specification, you actually estimate those paths and fix the variances. But we're not going to do that. We're not going to do that. We're going to use this kind of specification pretty much all the time, I think.
Sorry, can you explain what the disturbance variance free means one more time?
Okay, so it means we're going to freely estimate the disturbance variance. So if we think, we haven't really talked about what parameters we're estimating here, but we're going to actually estimate this disturbance variance. So we're going to estimate this A path, and we're going to estimate this B path, and we're going to estimate this C path. Like when you think about what parameters we're going to get from the model, we're going to get an A, we're going to get a B, we're going to get a C, and we're also going to get the variance of U and the variance of V. And that's what I mean here by, whoops, let me go back. That's what I mean here by the disturbance variance is free. So this path is fixed to be 1, which means that we're just going to estimate a variance here. We're going to get how much of the and remember, this variance is just saying how much of the variance in Y are we not explaining with our model? Which, by the way, let's just back up and think back to multiple regression for a second. What is R squared again? Who remembers what R squared is?
The variance that is explained.
Yeah, I mean, technically it's the proportion of variance in the model that is explained, right? And so this, the variance that isn't explained, this is just like, if you take the variance that isn't explained and you divide it by the total variance, you're going to get 1 minus r squared, right? Because again, r squared is technically a proportion. It's not, it's the variance explained divided by the total variance. This is the variance unexplained, right? So if you took like the total variance minus this u variance, it would give you the variance that is explained, which you could then divide by the total variance to get the r squared. So this is very much related to sort of r squared. But instead of sort of thinking about how much are we explaining, we're thinking about like how much variance are we not explaining? And then we can easily take this, which is a variance, and turn it into something like 1 minus r squared, right? We take this, divide it by the total variance in y, and it's going to give us 1 minus r squared. And then obviously if we do that, then we can easily get what r squared is as well. Does that make sense? Okay. So let's talk about how many, and then really should, okay, how many parameters are we estimating? So let's look back to this model that we were talking about. So what are the unknowns? I'm going to talk about knowns and unknowns when we start to think about counting parameters. So how many parameters are we estimating in this model? Well, I didn't draw them in, and I wish I, but for every exogenous variable, we're always going to estimate a variance. Like there's always going to be it's exogenous, right? So nothing else is going on, but it is going to, it's a variable, so it's going to vary. So it's going to have a variance. So we're going to estimate a variance for every exogenous variable. So here I'm saying, okay, we're estimating 3 exogenous variances, 1 for motivation, 1 for academic self-perceptions, and 1 for self-regulation. I'm also estimating 1 endogenous variance. That is the same thing as the disturbance variance. So in this case, it's the variance of E. So for GPA, I'm not actually estimating the variance of GPA, but I'm estimating the variance in GPA that's not explained by those 3 predictor variables. That's what the E is. So it's the unexplained variance in GPA. And then of course, if I have the variances in those variables, how well they predict GPA and how much of GPA is unexplained by those variables, I can always use those to recreate what the total variance is. Okay, so I've got 3 exogenous variances, 1 endogenous or disturbance variance, so that's 4. I have 3 paths. Those are the paths from motivation, academic self-perceptions, and self-regulation to GPA. Okay, so that's the 3 paths. And then I have 3 covariances or correlations. Those are the covariances or the correlations among the exogenous variables. So you can see that, right? See that, and oh, by the way, just ignore the intercept for right now. I have the intercept in my equation below, but for right now, remember I said the first half of the semester we're not going to deal with means. So we're not going to deal with means and intercepts right now. So just ignore the beta 0. We're not going to, with the amount of unknowns change if GPA were a latent variable. Oh, well, yeah, Hannah, that's kind of, yes, it would. We'll talk about that in a minute. I mean, if it were a latent variable, then it would have to have measured, we'd have to have some measured variables that it predicts, right? And so that's going to change the total number of variables in the whole model, right? And it will change that, it will definitely change how things go. And we have an example of that shortly, but so sort of table that thought, but you're right. So for now, let's just think about these 4 known variables. So, okay, so we're estimating, again, don't think about means and intercepts. So we're estimating 3 exogenous variances, 1 disturbance variance, 3 paths, and 3 covariances or correlations. So we're actually, we're going to be estimating 10 parameters in our model. Yes, Fayez.
Question about the endogenous variable. Here we consider disturbance as the endogenous variable, right?
Not endogenous variable, endogenous variance. I mean,
Oh,
GPA, yeah, GPA
So
is,
that's different.
yeah. GPA is our endogenous variable. And that little e is our endogenous variance. It's the piece of GPA that is not explained by the other variables. So yeah, there's a difference between GPA is the endogenous variable. The disturbance is the endogenous variance. Does that make sense?
Yeah, I got confused because of the equation that we wrote for the z variable in the other slide. That we wrote the equations for z and y.
Mm-hmm.
In that equation, after we replace y with the other two variables, we said that okay, all the variables in the equation are exogenous variables. But
That's
we
true.
still had the endogenous variance of the endogenous variable, right?
Yeah. I guess so. I suppose to be what I should have said is only what I meant was only the exogenous. Well, I stand by what I said. Only the exogenous variables were in there, but you're right that the endogenous variance of y was in there, right? But that's not actually, again, that's not a variable in our model. If you think about what I was saying, it's like the endogenous variables, x1 and x2 are in there, and then yes, there are endogenous variances in there, but we didn't make any reference to that y variable at all, only to the piece of y that wasn't predicted by x1 and x2. So like we had reframed that equation as being a function of our exogenous variables and these other parameters that we're estimating.
Gotcha.
Yeah? Does that make sense?
Yes, thank you.
Sure. Okay, so now the question is, okay, these are our unknowns. So we're estimating 10 parameters, but what are our knowns? How many parameters can we estimate, right? I mean, and so this is where things are, I think, really interesting in structural equation modeling. So we're going to think about the total number of knowns as the number of unique elements in the variance covariance matrix. So the variance covariance matrix, which again, for the first half of class is going to basically, that is going to be what's called a sufficient statistic, which means everything that we need to know to do this analysis is going to be contained in that variance covariance matrix. By the way, I should have probably mentioned that as an advantage of SEM. So this is kind of cool because if you have the variance covariance matrix, you can actually run these models. You don't have to, I mean, you could have raw data, but you don't have to have raw data. You could literally just have a variance covariance matrix and run the models. Because what we're really doing is we're starting with that variance covariance matrix, and we're really looking at sort of, how well can we reproduce that variance covariance matrix. So then the number of knowns here, it has nothing to do with the number of people. We could have 50 people or 500 people or 5,000 people, but we can't estimate more parameters than we have unique elements in the variance covariance matrix. So how many unique elements are there in the variance covariance matrix? Well, just think about if you ran a little correlation matrix, right? And you have 4 variables. So you get a little 4x4 matrix, right? So how many unique elements? Let's see, I don't think I have a picture. Oh yeah, there we go. I do have a picture. All right, so how many unique elements are there in that variance covariance matrix? So we've got, again, you've got this is not a correlation matrix, this is a variance covariance matrix, so it's unstandardized. So there's a variance for motivation, there's a variance for academic self-perceptions, there's a variance for self-regulation, and there's a variance for GPA. So there are 4 variances. And then there are covariances among all of those variables, right? So there's the covariance between A and M, the covariance between S and M, covariance between G and M, right? So again, if you sort of think about we've got 4 variables, so we've got this little 4x4 matrix, and we've got 4 variances, and we've got 6 covariances. And the reason I left everything above the diagonal blank is because, remember, the covariance of GPA and motivation is the same as the covariance of motivation and GPA, right? So those are not unique elements. You get like repetition above the diagonal, right? So there are 10 unique elements in our variance covariance matrix. Great. So we have 10 unique elements in our variance covariance matrix. And we said we had 10 pieces of information that we actually wanted to estimate, right? So we have 10 knowns. Those are the number of elements in the variance covariance matrix minus 10 unknowns. And what does that mean? It means that we can figure out what are the number of degrees of freedom in this model. And the number of degrees of freedom in the model are always going to be the knowns minus the unknowns. So in this case, it's really easy. 10 minus 10. How many degrees of freedom are in this model? 0. So this is what we call a just identified model. It means that we can perfectly reproduce, like we can perfectly reproduce this variance covariance matrix with our set of 10 parameters. So again, this is called a just identified model. We're not going to get any model fit information for models that are just identified because we can perfectly reproduce the variance covariance matrix with our set of parameters. This is also, by the way, a multiple regression model, right? Every multiple regression model is a just identified model. That's why you never thought about model. That's why you never counted the number of parameters when you were doing multiple regression, because it would have been really boring, because every model would have given you 0 degrees of freedom. It would have been a just identified model. It fits perfectly, fit in the sense that you can perfectly reproduce the variance covariance matrix with your unknowns because you have exactly as many unknowns as you have knowns. So we're doing this for a multiple regression model, but you never probably did it before because it wasn't very interesting to do before. Yes, Claudia.
Just to recap, you said that we have 10 knowns, and because we have 10 knowns, that implies that we have 10 unknowns.
No, I already counted.
Yeah.
I mean, I counted. No, you could have 10 knowns and you could have fewer than 10 unknowns. I counted the unknowns over here first. I said we have 3 exogenous variances, we have 3 covariances, we have 3 paths, and we have 1 disturbance variance. So I know that there are 10 unknowns because I counted them here. But here, that's a good, Claudia, just to go with what you're saying. Imagine this. Imagine I said, you know what? I don't believe, this is funk, by the way, but let's say I said, I don't believe that academic self-perceptions are correlated with self-regulation at all. So I don't want to allow there to be a correlation between those 2 exogenous variables. Then how many parameters would I be estimating in this model? If I said I'm not going to allow there to be a correlation between academic self-perceptions and self-regulation, I'd be taking out one of those curved arrows, right? How many unknowns would I have? Anybody?
9.
9, exactly. What I'd be doing there is actually constraining, and again, we'll talk about whether, what this does, but I'd be constraining that correlation to be 0. I'm not allowing for there to be a freely estimated path there anymore. I'd have 9 unknowns. And if I did that, then when I come over here, again, if I got rid of that one if I got rid of that one correlation, now I would actually have 1 degree of freedom because I'd still have 10 knowns, but I'd actually now have 9 unknowns. And so that would give me 1 degree of freedom. And now I could actually test the fit of that model. So again, that's not something you ever did in regular multiple regression, because you just it's automatically in regular multiple regression, all of the exogenous variables are by default always correlated with each other. But in a path model like this, it would be very easy for me to start with a multiple regression model like we just did and say, well, wait a minute, what would the fit look like if I said academic self-perceptions and self-regulation are completely uncorrelated, right? And now I've got a model that has a degree of freedom, and I could actually compare those two models to each other to see which of those models fits better. Is it reasonable to say those, which by the way, it wouldn't be, but is it reasonable to say that those two variables are not related to each other? I saw a couple things flash, but I didn't get to read them. So let me see.
He was asking where we got the 10 knowns, and I said it was the variance covariance matrix. And you
Yeah, I literally counted them. I just counted the elements, the unique elements in this little blue box, right? So I've got 4 variances and 6 I've got 4 variances and I've got 6 covariances. And so now imagine if I had a 5 by, if I had five variables in my model, right? I'd have 5 variances and I would have 10 covariances. So I would have 15 unique pieces of information. Now, at a certain point, it would be really tedious to have to draw out the variance covariance matrix and count all the elements. So like, what if I said there are 100 variables in my model? How many unique variances and covariances are there? Like, you could actually, do you want to do that? You don't want to do that, right? Like, I'm going to draw this 100 by 100 matrix. So there's a really easy trick to compute that, which I think, let's see, do I have it written down here so I don't have to? No, I don't have it written down here. There's a really easy trick to compute that, and it's just you take the number of variables. I really wish I could write on this thing, which I can't. You take the number of variables times the number of variables plus 1 divided by 2, and that'll give you the number of unique elements. I know I have that formula a few slides up, so we'll go back to that. But don't stress, there's an easy way to figure out what the number of knowns are without actually having to like draw out the variance covariance matrix. But that's really what we're doing. We're figuring out how many unique elements are there in the variance covariance matrix. Any other questions to this point?
And then I was getting to Amanda. She said, why is there an E above the endogenous GPA variance, but no separate labels for the exogenous variances? And she says that she's confused. Oh, hold on. That there is an E for the unknown, but the var G in the covariance matrix is known.
I'll just jump in, Jocelyn. So I think what I'm confused is, so E is being called out separately, but not having labels on like motivation, self-perception for those variances. So if E and variance of G are actually the same, how is that so when one is known and one is unknown?
Well, they're not the same. They're not the same. But so remember, I showed a little thing where I said we could do I could put little double-headed arrows above each of these boxes to show that we're estimating a variance for each exogenous variable. Often people don't do that because it's just assumed every time you've got an exogenous variable, you're going to estimate a variance for it. You have to. It's a variable. It's going to have a variance. But so we're estimating a variance for each exogenous variable. But that is different from what we're doing here with GPA. This little E is not indicating that we're estimating the variance of GPA, but rather it's indicating that we're estimating the variance in GPA that isn't explained by the exogenous variables. And that's, so basically for every variable in the model, we are going to estimate some sort of variance, right? There's going to be a variance of some sort, but there are 2 different kinds of variances. If it's an exogenous variable, we're just going to estimate like a good old garden variety variance. Like how much variance is there in this exogenous variable? And that's all we can do because nothing's predicting it. So it's just like, how much variance is there? But if it's an endogenous variable, then we're not actually estimating the total variance anymore. We're just estimating the piece of the the piece of variance that isn't explained by the other variables in the model. then we could get the total variance. You know, we could always then take that to get the total variance if we wanted to. But what we're actually estimating as a parameter when it's an endogenous variable is the piece, the variance that isn't explained by the other variables in the model. Does that make sense?
Yeah, thank you.
Okay, good.
Should we follow suit and not do the arrows, the curved arrows above variables in our diagrams?
It really doesn't matter. You'll see that at times I do it and at times I don't. I would say, I mean, if it helps you to remember that you're estimating a variance, then feel free to do it. If you don't feel like you need it, you don't need to do it. There are times when you get to really much more complicated models where it probably is like a little bit helpful to just be as explicit as possible. But for these kinds of models, it's not really going to matter. But what is going to matter is just remember that if you've got an exogenous variable, for every exogenous variable, you're going to estimate a variance for that exogenous variable. Yeah. So whatever works for you. Other questions? I think this is probably a good point to take a break if there aren't any other questions. So let's take about 10 minutes. We'll come back around, 11:15, and that'll give us like 1 more hour to plow through a bit more of this foundational stuff. Sound like a plan? All right, so I'll see you in about 10 minutes. There we go. Share content, PowerPoint, share. Uh-oh. Oh, shoot. Okay, there we go. All right, so I think we're ready to get back to it. So now, what about if we had a latent variable structural equation model of academic achievement? And by the way, GPA here could be, I mean, you could have like a latent variable for your endogenous variable too. So you could have a latent variable called achievement, for example, and it could be measured by a bunch of different observed variables. But for right now, just for this, for the purposes of this model, we're going to assume that the GPA is still an observed variable. So it's, you know, GPA is an observed variable in our model. But instead of measuring motivation with a subscale and academic self-concept with a subscale and self-regulation with a subscale, instead we want to use latent variables to measure. We're using latent variables for those 3 constructs. So the motivation construct is a latent, you know, is a latent variable, right? I have this latent motivation variable, and there are 4 different motivational measures. Maybe those are 4 different, let's say there are 4 different motivational scales or subscales, or they could be anything, right? But let's just say there are 4 different subscales that measure different aspects of motivation. And for academic self-concept, I have the same thing here. I have 4 different, let's say, scales or subscales that measure academic self-concept. And now academic self-concept is my latent variable. And now I have self-regulation also as a latent variable. And there are 4 different self-regulation measures here that measure self-regulation. So let's start by thinking about how many knowns are there. Remember, the knowns are the number of unique elements of the variance covariance matrix. So to figure that out, we first have to figure out how many variables are there, and then we'll have to figure out how many unique elements there are in the variance covariance matrix. So how many observed variables are there? And remember, the observed variables are our boxes. There are rectangles and our squares. So how many observed variables are there? Again, think about variables that are actually going to be in my data file. So how many observed variables? 13. Good job, Mara. There are 13 variables here, right? There are 4 observed variables for motivation, 4 for self-concept, 4 for self-regulation. That takes us to 12, plus GPA is our 13th observed variable. So there are 13 observed variables here. Now let's see if I still don't have it on my, okay, hold on. See if I can switch to my whiteboard here quickly, maybe.
What about that little image? Are you trying to draw?
Yeah, I was going to draw.
Oh,
So what I wasn't going to draw. I was going to say, so we have 13. I wanted to show that. So we have 13 variables. I wanted to show that, variables. I wanted to show that equation. So how many unknowns, or sorry, how many knowns? How many unique elements of the variance covariance matrix? So the number, hold on. Okay, so the number of unique, what's going on? I'm not that bad at writing. Let's try this again. The number of unique variances and covariances is equal to the number of variables, so I'm going to call that V, times the number of variables plus 1 divided by 2. So with 13, it's going to be 13 times 13 plus 1 is 14. And 13 times 14 divided by 2 is 13 times 7, which is 90. What is 13 times 7? 91, right? Tell me if I'm wrong about my simple arithmetic here, but I think that's 91, isn't it? Okay.
You're correct. It's 91.
All right, good. So 13 times 14 divided by 2. I should always have a calculator next to me. I always say it's so much easier to do this stuff in your head when you're not like teaching it. You know, when I'm sitting and listening to somebody else, I'm like, big bang boom in my head. But when I'm like in front of a crowd and I have to do basic arithmetic, I kind of freeze a little. So if I mess up, please always correct my arithmetic. Okay, so that's 91. So that is our number of knowns. That's how I compute my number of knowns. And you might be thinking to yourself, why does that formula work? Is anybody thinking that? Maybe you don't care, I don't know. But it does work because where did the 2 come from? The divided by 2? Okay, so here's how it works. If you think about it, the V times, how to think about this best? The V, okay, V times V minus 1, okay? If you take V times V minus 1, that is actually going to give you the number of the number of off diagonal elements. Not writing, hold on. There we go. So V times V minus 1 gives you the number of off diagonal elements. But you really need to count the variances. You want to count the diagonals. So that would be V times v minus 1 plus v would actually give you all of the squares. But you also don't want to count the redundant. Remember, you don't want to count the above diagonals. And that's actually where this divided by 2 thing comes from. So you take, like, if you think about it, you take v times v minus 1, right? And this plus v, that doesn't actually need to be, oops, that should be a minus 1, sorry. Just messed that up. That should be a minus 1. That should be minus 1, there we go. This v does not actually need to be divided by 2 because there's those, you always count the diagonals. So it's really like v divided by v minus 1, right? Or v times v minus 1, sorry, divided by 2, plus v. But if you kind of work out the algebra there, then that is v times v plus 1 divided by 2. So it's literally just a way to count up all of the elements that are in that variance covariance matrix. All right, but anyway, if you didn't follow that sort of shoddy explanation, don't worry, it doesn't matter. You really just need to be able to use the formula. But the formula is directly coming from this idea that we want to count up the unique elements below the diagonal plus the diagonal. Those are the things. And sometimes you might only care about the unique elements below the diagonal. And if you only care about the unique elements below the diagonal, that formula is v times v minus 1 divided by 2. So this formula will give you the number of correlations, the number of unique correlations. The v times v plus 1 divided by 2, this gives you the number of variances and covariances. Does that make sense? Okay, cool. And that's messy. So let's see. Now I can get rid of that, right? No, I don't want to save it. Okay, now I have to go back over. There ought to be a better way to sort of switch back and forth. I'll get this figured out by the time we're back in class. Oops, hold on, I got to share. Add, let me share first. Share, content, PowerPoint, share. Okay, there we go. Slide. Now we got to go back a sec. Okay, so we figured out the number of knowns here, right? We had 13 variables, and we said 13 times 14 divided by 2 is actually, or 13 times 14 divided by 2 is actually 91. So we know the number of knowns here is 91, right? We could also figure out the number of unknowns. So let's count up the number of parameters. That's the number of parameters we're actually estimating, right? Or the number of, so remember I said every exogenous variable, actually maybe we don't want to count up the unknowns. We'll count up the unknowns later. There's a complexity here that maybe I don't want to get into quite yet. We'll come back to the unknowns. Okay. So in our next, next, I want you to see if you can do this. Draw a path diagram to illustrate the following set of equations. Use boxes to represent the observed variables, circles to represent the disturbances, include paths and the path per, and label them as they're specified in the equation, and assume that the exogenous variables are correlated with each other, and assume that the disturbances are uncorrelated with each other and they're uncorrelated with the exogenous variables. So let's just take a minute and see if you can do this, and then we'll talk about it. Because this is exactly the kind of thing that you would be doing for homework this week. give you another minute or so. One thing I should have said too is often when people refer to path analysis, so I said draw a path diagram, and a path diagram is a very general term, but when people say path analysis, they're usually talking about a model in which you have only observed variables. So you have a system of just observed variables. And it's, you could say a path analysis with latent variables, I guess, but usually people will refer to, usually when people say path analysis, it's usually just observed variables. So this is actually a path analysis model. We don't have any latent variables. I mean, right, the disturbances are latent variables, but we don't have any sort of latent or conceptual variables, right? This model. Okay, so you should have gotten, maybe yours doesn't look as pretty as this if you weren't thinking about how to, you might not have put your X3 in the middle there. You might have put it somewhere else or whatever, but this is basically what your model should look like, right? So X1 and X2 are both predicting X3, and then X1, X2, and X3 are all predicting Y, and both X3 and Y have disturbance variances, right? We have the U and the V. And then again, I didn't show anything for those exogenous variances, but you could put those little double-headed arrows on X1 and X2 if you wanted to. Is it okay if the paths cross like they do here? Yeah, it's okay. I mean, there's no rule against paths crossing. It takes a little bit of experience and effort to kind of get things that look pretty. Sometimes often when I first draw something out, it looks a little uglier, and then I think, how can I make this so that it's a little bit clearer, right? But yeah, it's totally fine if the paths cross. Yes. Oh, just to be clear, what did that say? Sorry, can you read that, Jocelyn?
Yeah, just to be clear, the D path is from X2 to Y.
Yes.
Not U to X3.
Yes, very good point. Just to be clear, that is right. The D path, this is where sometimes when you use like a program, it gets a little weird. The D path is actually the X2 to Y, and that one that's right below the D is indicating that the path from U to X3 is actually 1. Just like you see that 1 right by the arrow for going into Y is saying that the path from V to Y is 1. But the D path is absolutely from X2 to Y.
And then but I believe she's referring to the equation when she asked this is, how do we know X1 and X2 are observable variables here? And I think she means in regards to like the equation, when you look at the equation, how do you know that X1 and X2 are observed variables?
Oh. Well, how do you know they're observed? If they were latent variables, we'd have a whole set of equations where we'd be predicting the observed variables from the latent variable. So I know they're observed. I know they're observed variables because there aren't any other, I know this sounds like a cheesy response, but there aren't any other variables, right? If X1 were a latent variable, then X1 would need to predict some indicators of that latent variable. Remember here, going back here. Let's go back here for a second. So over here, what we'd have is, gosh, I really wish I could write on this PowerPoint. There has to be a way to do that, right?
Is it that third button at the bottom left? Kind of looks like a paintbrush.
Let me see. Third button. Oh, yeah. I think you're right. Hold on. Let me
at
try
the
that.
bottom, yeah.
Let me try that. Oh, yeah, right, pen. Hey, I can do it. All right. So, but it's going to be ugly because I'm not going to be able to write very well. But here, you see how motivation predicts M1, M2, M3, and M4, right? So here we would actually have something that looks like this. M1 equals, you know, motivation, and actually we'd need a, say, a B times motivation, right? Plus E1. Do you see that's an E1 right there? So motivation, this M1, here it is. M1 is, I'm taking the variance in M1 and I'm attributing it to two sources. There's the variance in M1 that's explained by the latent variable motivation, right? And there's the variance in M1 that isn't explained by the motivation latent variable, and that's what's captured in this error variance of E1. And I would have the same thing here. I'd have M2, let's call this B1, is equal to, you know, each of these, there would actually be a loading here. There would actually be a, you know, there would be, we're going to estimate these things, right? So say B2 times motivation plus, see, I'm not so good at plus, oops, sorry, E2. So I would have, so if it were a latent variable, I would have to have an equation for each of my observed variables is a function of the latent variable plus error. Does that make sense? So going back to this question of, let's see if I can go back there. So going back to this question of how do I know that these are observed variables? I know they're observed variables because they're the only variables, right? I mean, there aren't any, if they were latent variables, then I would have observed variables that they're predicting. Any other questions about this path diagram? Does this make sense?
That's a question.
Yeah, so I have a question here, which is mostly just to kind of make sure that I'm thinking about this properly. Because part of what always gets confusing for me is that latent variables predict something else when we're actually using those observed variables to construct the latent variables. So when we're talking about paths, I'm assuming that we have the latent variables predicting the observed ones just because we can't get an actual measure of the latent one. So it's kind of like this, they're like the arrows and the way that they go are hard for me to think of because the observed ones are also making up the latent one.
I know what you're saying. So let me go back here.
Yeah.
So you're
I just want
saying,
to make sure I'm thinking of it correctly.
yeah. So I think that does throw a lot of people because you're right that we're using the observed variables to kind of, you know, come up with the latent variables. So sometimes people will say like, shouldn't the arrows go the other way around? Like the observed variables are predicting the latent variable, but that's not the way we're thinking of it. Like conceptually, the way we're thinking of it is there is this latent variable out there and I can't see it, but the latent variable predicts these indicators, right? And so, but there are actually models out there. So these are what are called reflective models, but you'll see that there are actually models, they get used in sociology more so than in other places, where they talk about like formative or causal indicators for latent variables. And probably the classic example of this would be something like SES, which SES is sort of, so in sociology, often SES, oops, let me go, might be, back to pen, okay. SES might be done like, oops, wait, go back, I wanted my pen. Okay, SES might look like this, SES. And you might actually have something like this where you have income, right? Okay, I'm not going to even try to write what's in the boxes, but income. And you also, oh my gosh, I don't know what I'm doing wrong with this pen here. Income, education, and parental occupational prestige, right? So this is like income, education, and parental prestige. And the idea here is this is like, these are what are called formative indicators because they're forming SES. And the idea here is that maybe this isn't like, it isn't the same kind of latent variable in the sphere of like, whoa, the truth is out there somehow, and I'm just getting these indicators to help me like understand this latent variable that I believe is real, but I can't actually measure directly. That's the way we're thinking of latent variables. Whereas in SES, it's like, I want this composite variable and it's going to be created from these 3 other variables. So there are places where people use latent variables that look more like this. Again, it comes up all the time in sociology, but in factor analysis, when we think about, like when we're thinking about constructs and latent variables, we're always sort of assuming that it's a real thing. I just can't see it. So I got to find these other ways to get at it. Does that make sense?
That does, yeah, and I think that helps
Okay.
clarify it for me because, yeah, I think I was getting caught up in that. Thank you.
Yeah, sure, no problem. But I agree. It seems really counterintuitive, I think, to people at first. Yes, Claudia.
I see that the numbers of indicators are the same for each of the latent variables that you have there. Is there's a rule for
No.
that?
That's a good point. Maybe I shouldn't have done that. I just did that to make it the example, but there's absolutely no rule that you have to have the same number of indicators. When we get more into the weeds, we'll talk about like what's the minimum number of indicators. But short answer to that is generally 3 is kind of your minimum, although you can get away with 2 sometimes, you know, if you've got multiple factors, but 3 is usually the minimum. But yeah, you could have 10 on one, 8 on one, 3 on another. It doesn't have to be the same number. Good question. Any other questions before we move along? Okay, so let's see where we were here. I don't need the pen anymore, right? Okay, we did that. All right. Okay, now this is going to be fun. So now, I mean, not that it wasn't fun before, but we're going to talk about Wright's rules to determine model implied correlation. So if you think about it, I've been talking about, these path diagrams, right? Maybe I want to know, I want to be able to recreate the correlation matrix. So for right now, we're going to talk about Wright's standardized rules. And imagine that I use the standardized regression coefficients now. Just to keep it simple, we're going to sort of think in standardized terms. We could do this with unstandardized, and maybe we will later on. But for now, let's just think about it as standardized. So imagine I have a path model, and I want to figure out what is the model implied correlation between 2 variables. I can actually use these tracing rules to figure out what the model implied correlation is between any 2 variables in the model. Okay, and here's how it works. It sort of sounds wonky at first, but it works really well. So no loops. That means you can't go through the same variable twice in one trace. So once you've gone through it once, you can't like loop back through it. And again, we're thinking about recursive path models right now. Let's keep it simple. Recursive path models, we're going to think about standardized coefficients and coming up with our model applied correlation. So we're not going to loop through the same variable twice in one trace. You'll see what that means. Don't go forward and then go backward. You can't, like when you're doing this tracing, you can't go forward and then go backward, but you can go backward and then go forward. And in fact, it's kind of a good idea to start at the end and trace your way backward. But you don't have to do that with the standardized tracing rules. You kind of have to do that with the unstandardized tracing rules. So that's why I say it's kind of a good idea. And this is going to permit linkages due to common causes. So those are upstream variables, but not due to common effects or downstream variables. And I have a good picture of this in a minute. And you can only use a maximum of 1 curved arrow between the paths. And what you're going to do is you're basically going to look at the path diagram. You're going to make all the possible traces between the 2 variables. And then you're going to sum all of those together to come up with what the model implied correlation is. And again, I know that sounds confusing, but I'm going to show you how to do it. So I think it'll make a lot more sense once we do it. Wait, that's not what I meant to do. Help, help. Okay, there we go. Where did my little buttons go? Okay, there we go. Okay, so let's start with this. You can go backward and then go forward, but not forward and then backward. So let's take this really simple model here. And let me see if I can get a pen and make it red maybe. So when I say you can go, what's the model implied correlation between X and Y here? Let's say we wanted to figure that out. I should have given these some letters. So let's call this A. We'll call this B, okay? So again, imagine that these are A and B are now standardized regression coefficients. Just to make things easy, we've got standardized regression coefficients, and I want to know what's the model implied correlation between X and Y. Well, I said I want to look at all possible, I'm going to sum all possible traces between two variables, and I said I can go backward and then go forward, but I can't go forward and then go backward. Okay, so I start at Y, and I can go back from Y to Z, and then I can go forward from Z to B, right? So now I've got A, and the compound path is just going to be this path multiplied by this path. So to get from Y to X, I go A times B times B. Okay, is there another way to get from X to Y or Y to X here? And that's it, right? I mean, this is the same. I mean, going this to this is the same as going this to this, right? B, X to Y is the same as Y to X. So now the model implied correlation between X and Y is actually just A times B, which, okay, let's put some numbers on that. So let's say this path is 0.6 and this path is 0.4, let's say. Again, these are standardized regression coefficients. That would be saying the correlation between X and Y is just 0.6 times 0.4, which is equal to 0.24. And I can do that because I can go backward and then forward. And it makes sense that these two variables, X and Y, they should be correlated with each other because they have a common cause, Z, right? And the higher these, if Z is really highly predictive of X and it's really highly predictive of Y, then it makes sense that X and Y have to be, reasonably highly correlated with each other, right? But now consider this. Let's go to the next picture. Okay, now here I've got X and Y, and notice I have not put a curved arrow between X and Y. So that really means that I'm saying that the correlation between X and Y is 0, right? So this lack of curved arrow means I'm not allowing for there to be a covariance between X and Y, which really means that the correlation between X and Y is 0, right? So now X and Y are both predicting Z, but how correlated are X and Y to each other? Well, 0, right? I just told you that. But you can't go forward and then go backward. You can see that it wouldn't make sense to be able to go forward and then go backward, because that would be saying here that X and Y are correlated with each other at A times B, but they're not. I just told you the correlation between X and Y is going to be whatever, if I allow a curved arrow here, it's going to be whatever that parameter is, right? Because they're exogenous, their correlation is just going to be their correlation. It's just going to be the correlation between the two variables. And in this case, I've said there is no correlation between the two variables. So it wouldn't make sense to be able, if you were to go forward and then go backward, you wouldn't get the right answer, right? The right answer is these aren't correlated with each other. So that's why that rule seems really funky. You can go backward and then forward, but not forward and then backward. But that's why, because you can't attribute, you do not want to be attributing, you don't want to be attributing sort of this A times B is not actually going to be the correlation between X and Y. But if you constrain yourself to only going backward and then forward, you can see if you start backward from Z and go to B, you get stuck at Y, right? And if you go backward from Z to A, you get stuck at X, and you can't get from X to Y, and the correlation is 0. So X and Y can both predict Z, but still be uncorrelated with each other. Does that make sense? Okay.
Not for me.
Yeah, I'm struggling
Yeah.
with the idea of going
Yeah.
forward and backward. I'm really confused about that. I'm sorry.
No, well, don't do it first. Don't go that's my point, is don't go forward and then go backwards. So just don't do that. But what I'm saying is, if you think about going backward here. If I'm saying you can go backward and then forward, but not forward and then backward, you can go backward from Z through to Y, right? Through B, that's fine. Then you can go backward from Z to A through X, but there's no way to actually connect X and Y to each other in this picture if you constrain yourself to only going backward and then forward, which is good because this picture is actually illustrating that there is no correlation between X and Y. So you shouldn't be able to get a correlation between X and Y because X and Y are both exogenous. Now, if I drew something like this, right? Let's say I drew this. It's really ugly. How do I get it? And now it's not 0 anymore, right? But let's say this is C. The correlation between X and Y in this picture would just be C. That's the only way to get from X to Y, would just be through this curved arrow. And basically, whenever you have two exogenous variables, there is really only going to be one linkage between two exogenous variables. If you think about it, they're exogenous because nothing else is going on. They're outside the model and they're predicting other stuff. So if you've got two exogenous variables, the only way they're ever going to be related to each other is through a curved arrow. Does that make sense? Yes, Eunice.
Hi, so I'm trying to figure out where Wright's rules would fit in. So this is for model implied correlations.
That's right. So this is for model implied correlations.
I'm sorry, but my training is always there should be no model implied. You should be using theory to build your model.
Theory is what you use to generate the model.
Yes.
And then the model, and then from the model, we're going to get these model implied correlations. So you're absolutely right that we start with theory. I'm not giving you any theory right now because I'm just trying to get you up and running on the technique. But of course, this would come from theory. So the theory generates the model, but then the question is, what are the model implied correlations? Let's just backtrack for a minute and remember that I said with a multiple regression model, we can always perfectly reproduce the variance covariance matrix. So we never needed to do this because we would always get like the model implied correlations would be the same as the actual correlations because we have as many knowns as unknowns. So it's not interesting. But in this model, let's just say, let me go back for a second. I wish I could erase this. There must be a way to, erase all ink on slide. There we go. So in this model, right, there's, let's start by thinking about counting our knowns and unknowns, okay? I have 3 knowns, right? So how many, three knowns, 3 variables is what I meant to say. We have 3 variables. So how many knowns do I have? 3 times 4 divided by 2, I have 6 knowns. So 6 unique elements of that variance covariance matrix, right? So my number of knowns is 6. Okay, so I'm just going to write a 6 here for a second. How many parameters am I estimating? Well, I'm going to count the number of variances, exogenous variances, 1 for X and 1 for Y. I'm going to count the number of paths. I got the A path and the B path. I'm going to count the endogenous variance here for Z, which is D. I've got 5 unknowns, okay? So 6 knowns and 5 unknowns, right? Which means I have 1 degree of freedom. Anybody have an idea? Where does that degree of freedom come from? Well, it comes from not by saying this correlation is 0, right? I said, no, X and Y are not, again, I'm doing that based on theory. I'm saying X and Y are not correlated with each other here. That's where I get my degree of freedom. And now the model implied correlations are saying like, okay, right? There are actually 6 variances and covariances. You're only actually using 5. I'm going to age myself here, but do you remember there used to be a show called Name That Tune? And they'd be like, hey, whatever the name of the host was, hey, Ralph, I can name that tune in 3 notes. You know, I can name that tune in 5 notes. So I'm kind of like, I can reproduce that model implied variance covariance matrix in 5 with 5 parameters instead of using all 6. With 6 parameters, I can reproduce it perfectly. But my model is more parsimonious. I can do it with 5 parameters. Okay, yeah, well, if I'm going to try to reproduce something that has 6 things with only 5, maybe it's not going to be perfect. How far off am I going to be? That's where this idea of model fit is going to come from. Does that make sense? Sort of?
Yes.
Okay, so when we talk about these model implied correlations, it's like one of the things we're going to be interested in is like, okay, I can figure out what the model implied correlations are, and then that tells me my model says the correlations are like this. How well does that relate to what the correlations actually are? If my model is good, they're not going to be exact, but they should be close, right? It would be nice if they were exact, but they're not going to be exact if it's not a just identified model. But my model implied correlation should be close to the correlations if my model is functioning well. If my model implied correlations are really different from the actual correlations, it tells me that there's a problem with my model. And so that's one of the reasons why we're going to be really interested in these model implied correlations. Because we're going to compare them, you know, explicitly or implicitly to our correlations. All right, let's try, if there aren't any, were there more questions that I didn't? Let's go to this, let's try that. Let's do a couple of these because I think doing them will make it like sink in a lot better. Okay, so here we go. So the model implied correlation between any 2 variables is the sum of the compound paths connecting those 2 variables. And again, we're going to remember that we can go backward and then forward, but not forward and then backward. So let's start by let's start with something easy. What's the model implied correlation between x1 and x2? That's a really easy one. How can you get from x1 to x2? What are the possible ways with the sort of the rights rules that I gave you?
Emily said R.
R, thank you. That's the only way, right? So the model implied correlation between x1 and x2 is just R. No problem, right? Okay, so that's good. Now let's try, what's the model implied correlation between x1 and y? So how can I, using those tracing rules, how can I get from x1 to y? Well, the first way is really obvious, right? There's A. So x1 and y, right? The first way is A. Is there another way that I can get from x1 to y using a maximum of 1 curved arrow per trace and not going right and going backward and then forward, but not forward and then backward? Okay, B times R. That's right, exactly. I can start at Y and I can go backward from Y to X2, and that's B. And then I can go through that curved arrow from X2 to X1, and that's R. And so the other way is B times R. So what is the model implied correlation between X1 and Y? Is the sum of those 2 things that we just said. It's the sum of A and B times R. So here we go. It's A plus B times R is going to be the model implied correlation. I'm not going to write model implied correlation because I won't be able to write it very well, but that's the model implied correlation between, I'll just put an R there, okay? That's the model implied correlation between X1 and Y. Now, what about the model implied correlation between X2 and Y? Well, one way we can get from X2 to Y is B, right? And the other way is A times R, right? So B plus A times R gives us the model implied correlation between X2 and Y. So far, so good? See, it's easier when you actually like do it, right?
No,
Now
no,
let's
Betsy, this made it worse for me. Now I have less idea of what's going on.
Oh no!
Yeah. So okay, I thought you had like your second question was figuring out the path for X1, and then everyone was saying that R and B get you there, but I thought
No, it wasn't figuring out the path for X1. It was figuring out the model implied correlation between X1 and Y, which is a different thing. The path from X1 to Y is just A. So
okay.
like, and those mean two different things. And so let's just go back and remind ourselves what those mean, because that's important. So A tells me how well does X1 predict Y after controlling for X2? And see, this is the thing. Remember, like in a multiple regression, our regression coefficients are always after controlling for the other variable. So like, I can't look at A and say, how correlated are X1 and Y? Not even like, what's the model implied correlation between X1 and Y, right? So what I can say is, after controlling for X2, this is the independent contribution of X1 on Y. But I want to know, hey, what's the model implied correlation between X1 and Y? And if you think about it that way, I need to not just look at the independent contribution of X1 on Y, but I also need to look at how much X1 and X2 are correlated with each other. That's the R. And then how much X2 predicts Y, that's the B. So if I really want to understand, like, how much are X1 and Y correlated with each other, at least, again, the model implied correlation. So what correlation does this model that I've drawn imply about X1 and Y? It's not just A, it's A plus R times B. Does that make sense?
Yeah, that helped a lot putting it back in the regression terms. Thank you.
Yeah, sure, no problem. How about everybody else? Good? Okay, so let's do a slightly more complicated one. Let's talk about what's the model implied correlation between X1 and Z. Okay, so let's think about this. What are the different ways I can get from Z to X1? Well, the first way is going to be to go back through Z to Y and Y to X1. So it's going to be the C path times the A path. Does everybody see that? So the first way is C times A. But there's another way too, right? I could go back through the C path to Y and then do exactly what we were just talking about, right? Y to X2, which is B, and X2 to X1, which is R. So the model implied correlation between Z and X1 is actually C times A plus C times B times R. And again, that's telling us, what does this model imply about the correlation between X1 and Z? And that's really interesting, I think, because what is the direct path from X1 to Z in this model? Well, there is no direct path, right? So, and anytime you don't have a path or you don't have a curved arrow, when there's white space, I always like to say, people always focus on like the paths that are there, but actually a lot of the action is in the paths and the correlations that aren't there. Because anytime you have white space, you're actually saying there's no correlation or there's no direct path. So here, because there's no direct path from X1 to Z, we're saying the direct effect of X1 on Z is actually 0. which really means after controlling for y, right, that there's no, and again, this is like a complete mediation model if you're familiar with mediation. So we're saying after controlling for y, x1 does not predict z. But that doesn't actually mean that x1 is unrelated to z, right? It just means that after controlling for y, x1 doesn't directly predict z. And so what I want to know is, yeah, what's the model implied correlation between x1 and z? And so to get that, then I'm going from, right, z to y, y to x2, x2 to x1 for that one pathway. And then I can also go from z to y and y to x1. Does that make sense? And then we add those two, yeah.
Compound paths help you see the arrows that aren't there.
Well, I don't know if, I mean, they don't enter into, I'm just saying, hold on. So it's CA, right, plus C times B times R. I guess I'm saying the arrows that aren't there imply something very specific. It's saying there is no direct path. So I could do something like this. I could draw this and say the path is 0. That's actually equivalent to not having the path at all. So where there's no path, I'm really just saying that direct effect is 0. There is no direct pathway there. And that's a place, again, so much of this is like, how can my model be wrong? Well, that's a place where my model can be wrong, right? Like there are two really clear places on the thing that I've drawn here where my model could be wrong. Like my model is actually saying there's no direct effect of x2 on z, and there's no direct effect of x1 on z. The only way that x1 and x2 actually affect z is through y. And if that's true, and my model is right, great, right? But if that's not true, my model's not going to fit very well because I'm not going to actually be able to correctly capture the action. Like my model implied correlations aren't going to look like the actual correlations because I'm making these constraints that actually aren't, they're not correct, right? And so like x1 and z would be, if this model isn't right, x1 and z would be more correlated in real life than my model implied correlations would suggest, for example. Yeah? Curious why I have to add it.
The compound paths.
So why do you have to add it? Because these are all the different pieces that are kind of entering into that model implied correlation. The model implied correlation isn't, right? It is actually the sum of all of those different pathways because the correlation is sort of, it is creeping through all of those different pathways. I don't know how to explain that better right this second. But you're always going to want to add the compound paths. And this is for model implied correlations, by the way. We're going to talk about model implied total effects as well. Maybe we should talk about, well, I think I've got another slide to talk about direct, indirect, and total effects. But so this is for model implied correlations. Things will work a little differently when we talk about total effects. Okay, are we good? Does this make sense? Okay, let's see. Where are we? Okay, so we talked about this. What's the model implied correlation? We already did this. I should have used these slides. Look at that. They're so much prettier than everything I was just trying to scrawl, right? So you can see the model implied correlation between x1 and y is that A plus R times B, right? And then the model implied correlation between x1 and z is A, right? Oh, we already did this. Hold on, let me just go there. AC plus R times BC, R times B times C. Okay, so this is nice. So you have in your notes what I scrolled down in chicken scratch. So let's talk briefly about direct, indirect, and total effects, and then we'll leave it here for today because we only have about, I don't know, 7 or 8 minutes left. So direct, indirect, and total effects. So A direct effect, and you might be, again, if you've done anything with mediation, you're probably familiar with these terms. If you haven't, then welcome to direct, indirect, and total effects. So direct effect is when a path directly links two variables. So just think back to multiple regression. In a multiple regression model, if you have like three, remember we had those three independent variables predicting our dependent variable, and we had different paths. Those are direct effects. So there's a direct path from this variable to that variable. That's a direct effect, okay? Path directly links two variables. An indirect effect is a path that is between two variables that is actually transmitted via another variable. So it's like a mediational pathway. So going back to, let me go back to our picture here for a second. So there's a direct effect of x1 on y, it's A. There's a direct effect of x2 on y, it's B. There is no direct effect of x1 on z here in this model, right? Because there's no direct pathway. So the direct effect of x1 on z in this model is 0. There is no direct effect the way this model is drawn. It's like, no, there's no direct effect. And what this model is then saying is any effect of x1 on z is transmitted through y. Y is that intermediate variable or that mediator that transmits the effect of x1 on y. So what's the indirect effect of x1 on y? Okay, so let's go back to our slide there for a second. So the indirect effect is going to be the path between two variables that's transmitted via another variable, okay? But for indirect effects, oops, let me go back. For indirect effects, unlike model implied correlations, and this sometimes throws people off a little bit at first, we're not actually going to backtrack through the curved arrows. The indirect effect is really just like, what's the effect of x1, the independent, like again, the unique sort of effect of x1 on z after controlling for x2. That's really what an indirect effect is. And that's why we're not going to like do the model implied correlation and go through the x1, x2 correlation, because we're just asking how much does x1 predict z indirectly after controlling for x2. Do you see does everybody see the difference? So the model implied correlation is just like a regular, I'm just trying to reproduce the simple, regular old bivariate correlation between two variables. When I talk about direct, indirect, and total effects, I'm talking about what's the unique, so this is much more like regression regression speak. What's like the unique contribution of x1 on z? Again, directly would be the direct effect. Indirectly through y is going to be the indirect effect. And the total effect is just going to be the direct plus the indirect effect. So in this case, what's the indirect effect of x1 on z? Anybody? How do I get from x1? Yeah, a times c. It's just a times c. So actually direct, indirect, total effects is a little easier, I think, than model implied correlations, because it's just tracing through the pathways. We don't have to think about these correlation pieces anymore. So the indirect effect of x1 on z is a times c. What's the total effect of x1 on z? Anybody? Well, we said the direct effect was 0, right? And the indirect effect is a times c. So Mara, you're right, it's a times c plus 0. But I can simplify that and just say a times c, right? Because a times c plus 0 is a times c. So in the case where there is no direct effect, the total effect is just going to be the sum of all of the indirect effects. Now, in this case, there is only one way to get from from x1 to z. But there could be something more complicated, like, let's see here. Okay, we could have something more complicated like this, for example. Okay. So imagine I said, what's the what is the direct effect of attitude toward exercise on weight loss? We'll start with the easiest thing. What's the direct effect of attitude toward exercise on weight loss? 0. Excellent, right? There is no direct effect because there is no direct pathway from attitude toward exercise to weight loss. So that's easy, right? But now, what is the indirect effect of attitude toward exercise on weight loss? Well, now we have to do the sum of the compound paths that link, right, that trace through attitude toward exercise to weight loss. So we got a couple of them here, right? What's the first way we can get from attitude toward exercise to weight loss? We could go across the top, right? So exactly, so 0.31 times 0.3, okay, which is 0.093. I really should have a calculator. I'm going to get in trouble pretty soon here. But what's another way that I can go from, yeah, okay, I saw Amanda. Can you read that out, Jocelyn, what Amanda said? It always disappears and then.
Yep, Amanda said 0.31 times 0.3, and then you're going to add negative 0.44 multiplied by 0.15.
Yeah, well, negative 0.44. So another indirect effect is this negative 0.44 times 0.15 times what? Times 0.31, right? To get from weight loss to attitude toward exercise, the second path is going to be negative 0.44 times 0.15 times 0.31. Does everybody see that? So then the total indirect effect is going to be hold on, 0.31 times 0.15 times negative 0.44. Hold on, I think I have this done on the next slide. So rather than really hurt myself, let's go to the slide where I actually have this done. Okay, so here you go. So the direct effect of attitude toward exercise and weight loss is 0. The indirect effect, so the total indirect effect is 0.31 times 0.3, which is 0.093, plus 0.31 times 0.15 times negative 0.44, which is actually negative 0.02. And that's kind of interesting if you think about it. So this is saying the more you like exercising, the more you exercise, the more you lose weight, right? Like sort of across the top. But then this is saying the more you like exercising, the more you exercise, but the more you exercise, the more food you eat, and the more food you eat, the less weight you lose, because there's a negative 0.44. So there's sort of these two paths from, feeling good about exercising to weight loss. One is, oh yeah, you're exercising more, but because you're exercising more, you're eating more food. And so that actually has a negative effect, right? So this pathway sort of through the food intake is actually slightly negative. This other pathway across the top is positive. The total indirect effect is 0.073. And then the total effect is the direct effect plus the total indirect effect here, this 0.073. So the total effect of attitude toward exercise on weight loss is 0.073. Does that make sense? Does everybody see that? Questions? Okay, so your homework for this week is actually, I think there are 5 problems on your homework. There are a couple of pictures of models. You'll have to say whether they're recursive or non-recursive. There are a couple of path diagrams where you're asked to do, I can't remember now, it's direct, indirect, and total effects, I think. Is that right? There's one path diagram where you do that. And then, so there are just a couple of questions that sort of relate to the things that we've taught, maybe exogenous versus endogenous variables. So there are just some basic questions related to what we've talked about this week. Should not take very long. Again, Jocelyn has office hours on Mondays from 9 to 10 and Tuesdays from 11 to 12. Collaborate, so you'll actually sign into Husky CT and go to the is it Collaborate? Am I saying that right? What's it called?
Yeah.
Blackboard Collaborate, right?
Yep.
If you have any trouble getting there, just shoot us an email and we can get you there. I will post oh yeah, I should stop the recording right now, but I will, hold on. Stop sharing, there we go. And stop. Did I not start recording again after the break? I thought I did. That could be bad. I would have sworn I did, but I don't see it. I don't see the record button right now. That's really strange. Okay. Oh, maybe.
It shows that it's being recorded, from my view.
Yeah, it's still saying meeting recording is in progress.
Yeah, I don't see the little record button. Oh well, it'll stop recording at the end anyway. Just don't listen to the last few minutes when I'm babbling about trying to stop the recording. You'll know to stop listening. Anyway, now I forget what the question was that we were talking about.
Huda made a mention that I guess the deadlines for the homeworks are from 2020.
Oh, they are?
Yeah.
Well, the homeworks are always due the following week. Oh, there might be deadlines in the actual Husky CT. I'll go in and change those. Sorry. So I'll go in and change the deadlines to the 2022 deadlines in Husky CT, but just know that the homeworks are always going to be due the following week. If you run into any problems, again, email me and we can set up a time to talk, or go to Jocelyn's office hours, either Monday from 9 to 10 or Tuesdays from 11 to 12. And like I said, I don't think this homework should take long. So if it's pretty basic, what we've talked about today, but if you're getting stuck on something, then either come see me or come see Jocelyn. That's kind of the point of the homework, is just to make sure that, like, right, if you're getting confused when you try to do it on your own, then just hop on and see one of us so we can get that all straightened out. Any other questions? And then we'll sort of pick up where we left off, and there's lots more to discuss in terms of the basics and fundamentals of path analysis and modeling. And then with any luck, we might actually start a little bit on confirmatory. My plan is that we'll start a little bit on confirmatory factor analysis next week too.
Buzz just asked if you could share the class recording.
Oh, yes. Well, that's what started me on the whole thing about trying to stop the class recording. Yes, I will definitely share the class recording. I will post it. It usually takes a couple hours for it to like show up. So I probably won't get it posted till later this afternoon, but I will definitely post the class recording so you can listen to it again. And one last thing, I just want to reemphasize, I super strongly recommend reading chapter 4 that is posted in the modeling book that the preprint of the modeling book that I wrote, the sort of the page proofs for that. Because again, you'll find that the first chapter aligns really closely with what we're talking about, what we talked about in class today, and uses the same, even more so than Klein. Like it really, right? It starts where I start, and it uses the same vocabulary. So reading chapter 4 of that book should, I hope, clarify any confusion as well. So if you're you should always read everything, right? But if you're only going to read one thing between now and next week, read the McCoach and Cintron chapter 4, because it's like totally what we just talked about. So it should really reinforce that. All right, my God, it's already 12:21. We're 6 minutes over. See you next week. Sorry about that.
Thanks, Betsy. Have a nice day.
Have a good rest of the day.
Thank you.